Ocean, Earth define. The ocean, also the sea or the world ocean, is the body of salt water that covers approximately 70.8% of the surface of Earth and contains 97% of Earth's water. An ocean can also refer to any of the large bodies of water into which the world ocean is conventionally divided. Separate names are used to identify 5 different areas of the ocean: Pacific the largest, Atlantic, Indian, Southern Antarctic, and Arctic the smallest. Seawater covers approximately 361 million km to 139 million sq mi of the planet. The ocean is the principal component of Earth's hydrosphere and therefore integral to life on Earth. Acting as a huge heat reservoir, the ocean influences climate and weather patterns, the carbon cycle, and the water cycle. Oceanographers divide the ocean into different vertical and horizontal zones based on physical and biological conditions. The pelagic zone consists of the water column from surface to ocean floor throughout the open ocean. The water column is further categorized in other zones depending on depth and on how much light is present. The photic zone includes water from the surface to a depth of 1% of the surface light, about 200 m in the open ocean, where photosynthesis can occur. This makes the photic zone the most biodiverse. Photosynthesis by plants and microscopic algae free-floating phytoplankton creates organic matter using light, water, carbon dioxide, and nutrients. Ocean photosynthesis creates 50% of the oxygen in Earth's atmosphere. This upper sunlit zone is the origin of the food supply which sustains most of the ocean ecosystem. Light only penetrates to a depth of a few hundred meters. The remaining ocean below is cold and dark. The continental shelf, where the ocean approaches dry land, is more shallow, with a depth of a few hundred meters or less. Human activity has a greater impact on the continental shelf. Ocean temperatures depend on the amount of solar radiation reaching the ocean surface. In the tropics, surface temperatures can rise to over 30 C86F. Near the poles where sea ice forms, the temperature in equilibrium is about 2 C28F. Deep ocean temperature is between 2 C28F and 5 C41F in all parts of the ocean. Water continuously circulates in the oceans, creating ocean currents. These directed movements of seawater are generated by forces acting upon the water, including temperature differences, atmospheric circulation wind, the Coriolis effect, and differences in salinity. Tidal currents originate from tides, while surface currents are caused by wind and waves. Major ocean currents include the Gulf Stream, Kuroshio Current, Appleton's Current, and Antarctic Circumpolar Current. Collectively, currents move enormous amounts of water and heat around the globe. This circulation significantly impacts global climate and the uptake and redistribution of pollutants such as carbon dioxide by moving these contaminants from the surface into the deep ocean. Ocean water contains large quantities of dissolved gases, including oxygen, carbon dioxide, and nitrogen. This gas exchange takes place at the ocean surface, and solubility depends on the temperature and salinity of the water. The increasing concentration of carbon dioxide in the atmosphere due to fossil fuel combustion leads to higher concentrations in ocean water, resulting in ocean acidification. The ocean provides society with important environmental services, including climate regulation. It also offers a means of trade and transport and access to food and other resources. Known to be the habitat of over 230,000 species, it may contain far more, perhaps over 2 million species. However, the ocean is subject to numerous human-caused environmental threats, including marine pollution, overfishing, and effects of climate change on oceans, such as ocean warming, ocean acidification, sea level rise, and many more. The continental shelf and coastal waters that are most influenced by human activity are especially vulnerable. Natural history. During planetary formation, Earth possibly had magma oceans. Subsequently, outgassing volcanic activity and meteorite impacts, according to current theories, produced an early atmosphere of carbon dioxide, nitrogen, and water vapor. The gases, and with them the atmosphere, are thought to have accumulated over millions of years, and after Earth's surface had significantly cooled, the water vapor over time would have condensed, forming Earth's first oceans. The early oceans might have been significantly hotter than today and appeared green due to high iron content. Geological evidence helps constrain the time frame for liquid water existing on Earth. A sample of pillow basalt, a type of rock formed during an underwater eruption, was recovered from the Isua Greenstone Belt and provides evidence that water existed on Earth 3.8 billion years ago. In the Novuagittuq Greenstone Belt, Quebec, Canada, rocks dated at 3.8 billion years old by one study and 4.28 billion years old by another show evidence of the presence of water at these ages. If oceans existed earlier than this, any geological evidence either has yet to be discovered or has since been destroyed by geological processes like crustal recycling. However, more recently, in August 2020, researchers reported that sufficient water to fill the oceans may have always been on the Earth since the beginning of the planet's formation. In this model, atmospheric greenhouse gases kept the oceans from freezing when the newly forming sun had only 70% of its current luminosity. By 3.5 Ga, Earth's magnetic field was established, which helped prevent the atmosphere from being stripped away by the solar wind. Since its formation, the ocean has taken many conditions and shapes, with many past ocean divisions and potentially at times covering the whole globe. During colder climatic periods, more ice caps and glaciers form, and enough of the global water supply accumulates as ice to lessen the amounts in other parts of the water cycle. The reverse is true during warm periods. During the last ice age, glaciers covered almost one-third of Earth's landmass, with the result being that the oceans were about 122 m400 ft lower than today. During the last global warm spell, about 125,000 years ago, the seas were about 5.5 m18 ft higher than they are now. About 3 million years ago, the oceans could have been up to 50 m165 ft higher. Geography. The entire ocean, containing 97% of Earth's water, spans 70.8% of Earth's surface, making it Earth's global ocean or world ocean. This makes Earth, along with its vibrant hydrosphere, a water world or ocean world, particularly in Earth's early history, when the ocean is thought to have possibly covered Earth completely. The ocean is shaped irregularly, dominating Earth's surface unevenly, allowing the discernment of Earth's surface into a water and land hemisphere, as well as the division of the ocean into particular oceans. Oceanic divisions. The major oceanic divisions listed below in descending order of area and volume are so named based on nearest continents, various archipelagos, and other criteria. Oceans are fringed with coastlines that run for 360,000 kilometers in total distance. They are also connected to smaller, adjoining bodies of water such as seas, gulfs, bays, bights, and straits. Seawater covers approximately 361 million km to 139 million sq mi and is customarily divided into 5 principal oceans, as below. Ocean ridges and ocean basins. Every ocean basin has a mid-ocean ridge which creates a long mountain range beneath the ocean. Together they form the global mid-oceanic ridge system that features the longest mountain range in the world. The longest continuous mountain range is 65,000 km, 40,000 mi. This underwater mountain range is several times longer than the longest continental mountain range of the Andes. Oceanographers state that less than 20% of the oceans have been mapped. Formation. The origin of Earth's oceans is unknown. Oceans are thought to have formed in the Hadean eon and may have been the cause for the emergence of life. Scientists believe that a sizable quantity of water would have been in the material that formed the Earth. Water molecules would have escaped Earth's gravity more easily when it was less massive during its formation. This is called atmospheric escape. Plate tectonics, post-glacial rebound, and sea level rise continually change the coastline and structure of the world ocean. A global ocean has existed in one form or another on Earth for eons. Physical properties. Volumes. The volume of water in all the oceans together is approximately 1.335 billion cubic kilometers, 1.335 sextillion liters, 320.3 million cubic miles. Depth. The average depth of the oceans is about 4 km. More precisely, the average depth is 3,688 meters, 12,100 ft. Nearly half of the world's marine waters are over 3,000 meters, 9,800 ft deep. Deep ocean, which is anything below 200 meters, 660 ft, covers about 66% of Earth's surface. This figure does not include seas not connected to the world ocean, such as the Caspian Sea. The deepest point in the ocean is the Mariana Trench, located in the Pacific Ocean near the northern Mariana Islands. Its maximum depth has been estimated to be 10,971 meters, 35,994 ft. The British naval vessel Challenger Roman II surveyed the trench in 1951 and named the deepest part of the trench the Challenger Deep. In 1960, the Tryst successfully reached the bottom of the trench manned by a crew of 2 men. Color. Oceanic zones. Oceanographers divide the ocean into different vertical and horizontal zones defined by physical and biological conditions. The pelagic zone consists of the water column of the open ocean and can be divided into further regions categorized by light abundance and by depth. Grouped by light penetration, the photic zone includes the oceans from the surface to a depth of 200 m. It is the region where photosynthesis can occur and is, therefore, the most biodiverse. Photosynthesis by plants and microscopic algae free-floating phytoplankton allows the creation of organic matter from chemical precursors including water and carbon dioxide. This organic matter can then be consumed by other creatures. Much of the organic matter created in the photic zone is consumed there, but some sinks into deeper waters. Below the photic zone is the mesopelagic or twilight zone, where there is a very small amount of light. Below that is the aphotic deep ocean, to which no surface sunlight at all penetrates. Life that exists deeper than the photic zone must either rely on material sinking from above sea marine snow or find another energy source. Hydrothermal vents are a source of energy in what is known as the aphotic zone depths exceeding 200 m. The pelagic part of the photic zone is known as the epipelagic. Grouped by depth and temperature, the pelagic part of the aphotic zone can be further divided into vertical regions according to depth and temperature. The mesopelagic is the uppermost region. Its lowermost boundary is at a thermocline of 12 degrees C, 54 degrees F, which generally lies at 700-1000 meters, 2300-3300 ft in the tropics. Next is the bathypelagic, lying between 10 and 4 degrees C, 50 and 39 degrees F, typically between 700-1000 meters, 2300-3300 ft, and 2000-4000 meters, 6600-13,100 ft. Lying along the top of the abyssal plain is the abyssopelagic, whose lower boundary lies at about 6,000 meters, 20,000 ft. The last and deepest zone is the hadalpelagic, which includes the oceanic trenchant, lies between 6,000-11,000 meters, 20,000-36,000 ft. The benthic zones are aphotic and correspond to the three deepest zones of the deep sea. The bathyal zone covers the continental slope down to about 4,000 meters, 13,000 ft. The abyssal zone covers the abyssal plains between 4,000 and 6,000 m. Lastly, the hadal zone corresponds to the hadal-pelagic zone, which is found in oceanic trenches. Distinct boundaries between ocean surface waters and deep waters can be drawn based on the properties of the water. These boundaries are called thermocline's temperature, halocline's salinity, chemocline's chemistry, and pycnocline's density. If a zone undergoes dramatic changes in temperature with depth, it contains a thermocline, a distinct boundary between warmer surface water and colder deep water. The tropical thermocline is typically deeper than the thermocline at higher latitudes. Polar waters, which receive relatively little solar energy, are not stratified by temperature and generally lack a thermocline because surface water at polar latitudes are nearly as cold as water at greater depths. Below the thermocline, water everywhere in the ocean is very cold, ranging from -1 degrees C to 3 degrees C. Because this deep and cold layer contains the bulk of ocean water, the average temperature of the world ocean is 3.9 degrees C. If a zone undergoes dramatic changes in salinity with depth, it contains a halocline. If a zone undergoes a strong vertical chemistry gradient with depth, it contains a chemocline. Temperature and salinity control the density of ocean water, with colder and saltier water being more dense, and this density in turn regulates the global water circulation within the ocean. The halocline often coincides with the thermocline, and the combination produces a pronounced pycnocline, a boundary between less dense surface water and dense deep water. Grouped by distance from land. The pelagic zone can be further subdivided into two subregions based on distance from land, the neritic zone and the oceanic zone. The neritic zone encompasses the water mass directly above the continental shelves and hence includes coastal waters, whereas the oceanic zone includes all the completely open water. The littoral zone covers the region between low and high tide and represents the transitional area between marine and terrestrial conditions. It is also known as the intertidal zone because it is the area where tide level affects the conditions of the region. Temperature. Ocean temperatures depend on the amount of solar radiation falling on its surface. In the tropics, with the sun nearly overhead, the temperature of the surface layers can rise to over 30 degrees C, 86 degrees F, while near the poles the temperature in equilibrium with the sea ice is about -2 degrees C, 28 degrees F. There is a continuous circulation of water in the oceans. Warm surface currents cool as they move away from the tropics, and the water becomes denser and sinks. The cold water moves back towards the equator as a deep-sea current, driven by changes in the temperature and density of the water, before eventually welling up again towards the surface. Deep ocean water has a temperature between -2 degrees C 28 degrees F and 5 degrees C 41 degrees F in all parts of the globe. Sea ice. Seawater with a typical salinity of 35 has a freezing point of about -1.8 degrees C 28.8 degrees F. Because sea ice is less dense than water, it floats on the ocean's surface, as does freshwater ice, which has an even lower density. Sea ice covers about 7% of the Earth's surface and about 12% of the world's oceans. Sea ice usually starts to freeze at the very surface, initially as a very thin ice film. As further freezing takes place, this ice film thickens and can form ice sheets. The ice formed incorporates some sea salt, but much less than the sea water it forms from. As the ice forms with low salinity, this results in saltier residual seawater. This in turn increases density and promotes vertical sinking of the water. Ocean currents and global climate. Types of ocean currents. An ocean current is a continuous, directed movement of seawater generated by a number of forces acting upon the water, including wind, the Coriolis effect, temperature, and salinity differences. Ocean currents are primarily horizontal water movements. They have different origins, such as tides for tidal currents or wind and waves for surface currents. Tidal currents are in phase with the tide, hence are quasi-periodic, associated with the influence of the moon and sun pull on the ocean water. Tidal currents may form various complex patterns in certain places, most notably around headlands. Non-periodic or non-tidal currents are created by the action of winds and changes in density of water. In littoral zones, breaking waves are so intense and the depth measurement so low that maritime currents reach often 1 to 2 knots. The wind and waves create surface currents designated as drift currents. These currents can decompose in one quasi-permanent current which varies within the hourly scale and one movement of Stokes drift under the effect of rapid waves movement which vary on timescales of a couple of seconds. The quasi-permanent current is accelerated by the breaking of waves and in a lesser governing effect by the friction of the wind on the surface. This acceleration of the current takes place in the direction of waves and dominant wind. Accordingly, when the ocean depth increases, the rotation of the earth changes the direction of currents in proportion with the increase of depth, while friction lowers their speed. At a certain ocean depth, the current changes direction and is seen inverted in the opposite direction with current speed becoming null, known as the Yakman spiral. The influence of these currents is mainly experienced at the mixed layer of the ocean surface, often from 400 to 800 meters of maximum depth. These currents can considerably change and are dependent on the yearly seasons. If the mixed layer is less thick 10 to 20 meters, the quasi-permanent current at the surface can adopt quite a different direction in relation to the direction of the wind. In this case, the water column becomes virtually homogeneous above the thermocline. The wind blowing on the ocean surface will set the water in motion. The global pattern of winds, also called atmospheric circulation, creates a global pattern of ocean currents. These are not only driven by the wind, but also by the effect of the circulation of the earth, Coriolis force. The sea's major ocean currents include the Gulf Stream, Horatio Current, Agulhas Current, and Antarctic Circumpolar Current. The Antarctic Circumpolar Current encircles Antarctica and influences the area's climate as well as connecting currents in several oceans. Relationship of currents and climate. Collectively, currents move enormous amounts of water and heat around the globe, influencing climate. These wind-driven currents are largely confined to the top hundreds of meters of the ocean. At greater depth, the drivers of water motion are the thermohaline circulation. The Atlantic meridional overturning circulation (AMOC) is part of a global thermohaline circulation. This is driven by the cooling of surface waters at northern and southern polar latitudes, creating dense water which sinks to the bottom of the ocean. This cold and dense water moves slowly away from the poles, which is why the waters in the deepest layers of the world ocean are so cold. This deep ocean water circulation is relatively slow, and water at the bottom of the ocean can be isolated from the ocean surface and atmosphere for hundreds or even a few thousand years. This circulation has important impacts on global climate and the uptake and redistribution of pollutants such as carbon dioxide by moving these contaminants from the surface into the deep ocean. Ocean currents greatly affect Earth's climate by transferring heat from the tropics to the polar regions and thereby also affecting air temperature and precipitation in coastal regions and further inland. Surface heat and freshwater fluxes create global density gradients that drive the thermohaline circulation, part of large-scale ocean circulation. It plays an important role in supplying heat to the polar regions, and thus in sea ice regulation. Oceans moderate the climate of locations where prevailing winds blow in from the ocean. At similar latitudes, a place on Earth with more influence from the ocean will have a more moderate climate than a place with more influence from land. For example, the cities San Francisco 37.8 N and New York 40.7 N have different climates because San Francisco has more influence from the ocean. San Francisco, on the west coast of North America, gets winds from the west over the Pacific Ocean, and the influence of the ocean water yields a more moderate climate with a warmer winter and a longer, cooler summer, with the warmest temperatures happening later in the year. New York, on the east coast of North America, gets winds from the west over land, so New York has colder winters and hotter, earlier summers than San Francisco. Warmer ocean currents yield warmer climates in the long term, even at high latitudes. At similar latitudes, a place influenced by warm ocean currents will have a warmer climate overall than a place influenced by cold ocean currents. French Riviera 43.5 N and Rockland, Maine 44.1 N have same latitude, but the French Riviera is influenced by warm waters transported by the Gulf Stream into the Mediterranean Sea and has a warmer climate overall. Maine is influenced by cold waters transported south by the Labrador Current, giving it a colder climate overall. Changes in the thermohaline circulation are thought to have significant impacts on Earth's energy budget. Since the thermohaline circulation governs the rate at which deep waters reach the surface, it may also significantly influence atmospheric carbon dioxide concentrations. Modern observations, climate simulations, and paleoclimate reconstructions suggest that the Atlantic meridional overturning circulation AMOC has weakened since the pre-industrial era. The latest climate change projections in 2021 suggest that the AMOC is likely to weaken further over the 21st century. Such a weakening could cause large changes to global climate. The waves and swell, the motions of the ocean surface, known as undulations or wind waves, are the partial and alternate rising and falling of the ocean surface. The series of mechanical waves that propagate along the interface between water and air is called swell, a term used in sailing, surfing, and navigation. These motions profoundly affect ships on the surface of the ocean and the well-being of people on those ships who might suffer from seasickness. Wind blowing over the surface of a body of water forms waves that are perpendicular to the direction of the wind. The friction between air and water caused by a gentle breeze on a pond causes ripples to form. A strong blow over the ocean causes larger waves as the moving air pushes against the raised ridges of water. The waves reach their maximum height when the rate at which they are traveling nearly matches the speed of the wind. In open water, when the wind blows continuously, as happens in the southern hemisphere in the roaring Forties, long, organized masses of water called swell roll across the ocean. 83-84 If the wind dies down, the wave formation is reduced. The size of the waves depends on the fetch, the distance that the wind has blown over the water, and the strength and duration of that wind. When waves meet others coming from different directions, interference between the two can produce broken, irregular seas. Constructive interference can cause individual unexpected rogue waves much higher than normal. Most waves are less than 3 and 10 ft high, and it is not unusual for strong storms to double or triple that height. Rogue waves, however, have been documented at heights above 25 meters 82 ft. The top of a wave is known as the crest. The lowest point between waves is the trough, and the distance between the crests is the wavelength. The wave is pushed across the surface of the ocean by the wind, but this represents a transfer of energy and not a horizontal movement of water. As waves approach land and move into shallow water, they change their behavior. If approaching at an angle, waves may bend refraction or wrap around rocks and headlands diffraction. When the wave reaches a point where its deepest oscillations of the water contact the ocean floor, they begin to slow down. This pulls the crests closer together and increases the wave's height, which is called wave shoaling. When the ratio of the wave's height to the water depth increases above a certain limit, it breaks, toppling over in a mass of foaming water. This rushes in a sheet up the beach before retreating into the ocean under the influence of gravity. Earthquakes, volcanic eruptions, or other major geological disturbances can set off waves that can lead to tsunamis in coastal areas, which can be very dangerous. Tides. Tides are the regular rise and fall in water level experienced by oceans in response to the gravitational influences of the moon and the sun, and the effects of the Earth's rotation. During each tidal cycle, at any given place the water rises to a maximum height known as high tide before ebbing away again to the minimum low tide level. As the water recedes, it uncovers more and more of the foreshore, also known as the intertidal zone. The difference in height between the high tide and low tide is known as the tidal range or tidal amplitude. In the open ocean, tidal ranges are less than 1 meter, but in coastal areas these tidal ranges increase to more than 10 meters in some areas. Some of the largest tidal ranges in the world occur in the Bay of Fundy and Ungava Bay in Canada, reaching up to 16 meters. Other locations with record high tidal ranges include the Bristol Channel between England and Wales, Cook Inlet in Alaska, and the Rio Gallegos in Argentina. Most places experience 2 high tides each day, occurring at intervals of about 12 hours and 25 minutes. This is half the 24 hours and 50-minute period that it takes for the Earth to make a complete revolution and return the moon to its previous position relative to an observer. Tidal force or tide-raising force decreases rapidly with distance, so the moon has more than twice as great an effect on tides as the sun. When the sun, moon, and earth are all aligned full moon and new moon, the combined effect results in the high spring tides. A storm surge can occur when high winds pile water up against the coast in a shallow area, and this, coupled with a low-pressure system, can raise the surface of the ocean at high tide dramatically. Water cycle, weather, and rainfall. Ocean water represents the largest body of water within the global water cycle. Oceans contain 97% of Earth's water. Evaporation. From the ocean moves water into the atmosphere to later rain back down onto land and the ocean. Oceans have a significant effect on the biosphere. The ocean as a whole is thought to cover approximately 90% of the Earth's biosphere. Oceanic evaporation, as a phase of the water cycle, is the source of most rainfall, about 90%, causing a global cloud cover of 67% and a consistent oceanic cloud cover of 72%. Ocean temperatures affect climate and wind patterns that affect life on land. One of the most dramatic forms of weather occurs over the oceans. Tropical cyclones, also called typhoons, and hurricanes depending upon where the system forms. As the world's ocean is the principal component of Earth's hydrosphere, it is integral to life on Earth, forms part of the carbon cycle and water cycle, and as a huge heat reservoir influences climate and weather patterns. Chemical composition of seawater. Salinity. Salinity is a measure of the total amounts of dissolved salts in seawater. It was originally measured via measurement of the amount of chloride in seawater and hence termed chlorinity. It is now routinely measured by measuring electrical conductivity of the water sample. Salinity can be calculated using the chlorinity, which is a measure of the total mass of halogen. Ions includes fluorine, chlorine, bromine, and iodine in seawater. By international agreement, the following formula is used to determine salinity. Salinity in equals 1.80,655 times chlorinity in the average ocean water. Chlorinity is about 19.2, and thus the average salinity is around 34.7. Salinity has a major influence on the density of seawater. A zone of rapid salinity increase with depth is called a halocline. The temperature of maximum density of seawater decreases as its salt content increases. Freezing temperature of water decreases with salinity, and boiling temperature of water increases with salinity. Typical seawater freezes at around -2 degrees C at atmospheric pressure. Salinity is higher in Earth's oceans where there is more evaporation and lower where there is more precipitation. If precipitation exceeds evaporation, as is the case in polar and some temperate regions, salinity will be lower. If evaporation exceeds precipitation, as is sometimes the case in tropical regions, salinity will be higher. For example, evaporation is greater than precipitation in the Mediterranean Sea, which has an average salinity of 38, more saline than the global average of 34.7. Thus, oceanic waters in polar regions have lower salinity content than oceanic waters tropical regions. However, when sea ice forms at high latitudes, salt is excluded from the ice as it forms, which can increase the salinity in the residual seawater in polar regions such as the Arctic Ocean. Observations of sea surface salinity between 1950 to 2019 indicate that due to the effects of climate change on oceans, regions of high salinity and evaporation have become more saline, while regions of low salinity and more precipitation have become fresher. It is very likely that the Pacific and Southern Oceans have freshened while the Atlantic has become more saline. General characteristics of ocean surface waters. The waters in different regions of the ocean have quite different temperature and salinity characteristics. This is due to differences in the local water balance, precipitation vs. evaporation, and the sea-to-air temperature gradients. These characteristics can vary widely among ocean regions. The table below provides an illustration of the sort of values usually encountered. Dissolved gases. Ocean water contains large quantities of dissolved gases, including oxygen, carbon dioxide, and nitrogen. These dissolve into ocean water via gas exchange at the ocean surface, with the solubility of these gases depending on the temperature and salinity of the water. The four most abundant gases in Earth's atmosphere and oceans are nitrogen, oxygen, argon, and carbon dioxide. In the ocean by volume, the most abundant gases dissolved in seawater are carbon dioxide, including bicarbonate and carbonate ions, 14 ml/L on average, nitrogen 9 ml/L, and oxygen 5 ml/L at equilibrium at 24 degrees C, 75 degrees F. All gases are more soluble, more easily dissolved in colder water than in warmer water. For example, when salinity and pressure are held constant, oxygen concentration in water almost doubles when the temperature drops from that of a warm summer day 30 degrees C, 86 degrees F to freezing 0 degrees C, 32 degrees F. Similarly, carbon dioxide and nitrogen gases are more soluble at colder temperatures, and their solubility changes with temperature at different rates. Oxygen, photosynthesis, and carbon cycling. The process of photosynthesis in the surface ocean releases oxygen and consumes carbon dioxide. This photosynthesis in the ocean is dominated by phytoplankton, microscopic free-floating algae. After the plants grow, bacterial decomposition of the organic matter formed by photosynthesis in the ocean consumes oxygen and releases carbon dioxide. The sinking and bacterial decomposition of some organic matter in deep ocean water at depths where the waters are out of contact with the atmosphere leads to a reduction in oxygen concentrations and increase in carbon dioxide, carbonate, and bicarbonate. This cycling of carbon dioxide in oceans is an important part of the global carbon cycle. The increasing carbon dioxide concentrations in the atmosphere due to fossil fuel combustion lead to higher concentrations in the ocean waters and ocean acidification. Dissolving atmospheric carbon dioxide reacts with bicarbonate and carbonate ions in seawater to shift the chemical balance of the water, making it more acidic. The oceans represent a major sink for carbon dioxide taken up from the atmosphere by photosynthesis and by dissolution. There is also increasing attention focused on carbon dioxide uptake in coastal marine habitats such as mangroves and salt marshes, a process sometimes referred to as blue carbon. Attention is focused on these ecosystems because they are strong carbon sinks as well as ecologically important habitats under considerable threat from human activities and environmental degradation. As deep ocean water circulates throughout the globe, it contains gradually less oxygen and gradually more carbon dioxide with more time away from the air at the surface. This gradual decrease in oxygen concentration happens as sinking organic matter continuously gets decomposed during the time the water is out of contact with the atmosphere. Most of the deep waters of the ocean still contain relatively high concentrations of oxygen sufficient for most animals to survive. However, some ocean areas have very low oxygen due to long periods of isolation of the water from the atmosphere. These oxygen-deficient areas, called oxygen minimum zones or hypoxic waters, could be made worse by the effects of climate change on oceans. Residence times of chemical elements and ions. The ocean waters contain many chemical elements as dissolved ions. Elements dissolved in ocean waters have a wide range of concentrations. Some elements have very high concentrations of several grams per liter, such as sodium and chloride, together making up the majority of ocean salts. Other elements, such as iron, are present at tiny concentrations of just a few nanograms 10⁻⁹ grams per liter. The concentration of any element depends on its rate of supply to the ocean and its rate of removal. Elements enter the ocean from rivers, the atmosphere, and hydrothermal vents. Elements are removed from ocean water by sinking and becoming buried in sediments or evaporating to the atmosphere in the case of water and some gases. Oceanographers consider the balance of input and removal by estimating the residence time of an element. Residence time is the average time the element would spend dissolved in the ocean before it is removed. Very abundant elements in ocean water like sodium have high rates of input, reflecting high abundance in rocks and relatively rapid rock weathering, coupled to very slow removal from the ocean because sodium ions are rather unreactive and very soluble. In contrast, other elements such as iron and aluminium are abundant in rocks but very insoluble, meaning that inputs to the ocean are low and removal is rapid. These cycles represent part of the major global cycle of elements that has gone on since the Earth first formed. The residence times of the very abundant elements in the ocean are estimated to be millions of years, while for highly reactive and insoluble elements, residence times are only hundreds of years. Nutrients. A few elements such as nitrogen, phosphorus, iron, and potassium are essential for life, are major components of biological material, and are commonly called nutrients. Nitrate and phosphate have ocean residence times of 10,000 and 69,000 years, respectively, while potassium is a much more abundant ion in the ocean with a residence time of 12 million years. The biological cycling of these elements means that this represents a continuous removal process from the ocean's water column as degrading organic material sinks to the ocean floor as sediment. Phosphate from intensive agriculture and untreated sewage is transported via runoff to rivers and coastal zones to the ocean, where it is metabolized. Eventually, it sinks to the ocean floor and is no longer available to humans as a commercial resource. Production of rock phosphate, an essential ingredient in inorganic fertilizer, is a slow geological process occurring in some of the world's ocean sediments, thus making mineable sedimentary apatite phosphate in effect a non-renewable resource CP. This continuous net deposition loss of non-renewable phosphate from human activities may become a resource problem in the future for fertilizer production and food security. Climate change. Marine life. Life within the ocean evolved 3 billion years prior to life on land. Both the depth and the distance from shore strongly influence the biodiversity of the plants and animals present in each region. The diversity of life in the ocean is immense, including animals. Most animal phyla have species that inhabit the ocean, including many that are only found in marine environments such as sponges, Cnidaria such as corals and jellyfish, comb jellies, brachiopods, and echinoderms such as sea urchins and sea stars. Many other familiar animal groups primarily live in the ocean, including cephalopods, includes octopus and squid, crustaceans includes lobsters, crabs and shrimp, fish, sharks, cetaceans includes whales, dolphins, and porpoises. In addition, many land animals have adapted to living a major part of their life on the oceans. For instance, seabirds are a diverse group of birds that have adapted to a life mainly on the oceans. They feed on marine animals and spend most of their lifetime on water, many only going on land for breeding. Other birds that have adapted to oceans as their living space are penguins, seagulls, and pelicans. 7 species of turtles, the sea turtles, also spend most of their time in the oceans. Plants, including sea grasses or mangroves, algae. Algae is a catch-all term to include many photosynthetic, single-celled eukaryotes, such as green algae, diatoms, and dinoflagellates, but also multicellular algae such as some red algae, including organisms like Pyropia, which is the source of the edible nori seaweed, and brown algae, including organisms like kelp. Bacteria, ubiquitous single-celled prokaryotes found throughout the world, archaea, prokaryotes distinct from bacteria, that inhabit many environments of the ocean as well as many extreme environments. Fungi, many marine fungi with diverse roles are found in oceanic environments. Human uses of the oceans. The ocean has been linked to human activity throughout history. These activities serve a wide variety of purposes, including navigation and exploration, naval warfare, travel, shipping and trade, food production, e.g. fishing, whaling, seaweed farming, aquaculture, leisure cruising, sailing, recreational boat fishing, scuba diving, power generation, sea marine energy and offshore wind power, extractive industries, offshore drilling and deep-sea mining, freshwater production via desalination. Many of the world's goods are moved by ship between the world's seaports. Large quantities of goods are transported across the ocean, especially across the Atlantic and around the Pacific Rim. A lot of cargo, such as manufactured goods, is usually transported within standard-sized, lockable containers loaded on purpose-built container ships at dedicated terminals. Containerization greatly increased the efficiency and decreased the cost of moving goods by sea and was a major factor leading to the rise of globalization and exponential increases in international trade in the mid to late 20th century. Oceans are also the major supply source for the fishing industry. Some of the major harvests are shrimp, fish, crabs, and lobster. The biggest commercial fishery globally is for anchovies, Alaska, pollock, and tuna. A report by FAO in 2020 stated that in 2017, data in 2017 showed that fish consumption accounted for 17% of the global population's intake of animal proteins. In order to fulfill this need, coastal countries have exploited marine resources in their exclusive economic zone, although fishing vessels are increasingly venturing further afield to exploit stocks in international waters. The ocean offers a very large supply of energy carried by ocean waves, tides, salinity differences, and ocean temperature differences which can be harnessed to generate electricity. Forms of sustainable marine energy include tidal power, ocean thermal energy, and wave power. Offshore wind power is captured by wind turbines placed out on the ocean. It has the advantage that wind speeds are higher than on land, though wind farms are more costly to construct offshore. There are large deposits of petroleum, as oil and natural gas, in rocks beneath the ocean floor. Offshore platforms and drilling rigs extract the oil or gas and store it for transport to land. Freedom of the seas is a principle in international law dating from the 17th century. It stresses freedom to navigate the oceans and disapproves of war fought in international waters. Today, this concept is enshrined in the United Nations Convention on the Law of the Sea UNCLOS. There are two major international legal organizations that are involved in ocean governance on a global scale, namely the International Maritime Organization and the United Nations. The International Maritime Organization IMO, which was ratified in 1958, is responsible mainly for maritime safety, liability, and compensation, and they have held some conventions on marine pollution related to shipping incidents. Ocean governance is the conduct of the policy, actions, and affairs regarding the world's oceans. Threats from human activities. Human activities affect marine life and marine habitats through many negative influences, such as marine pollution, including marine debris and microplastics, overfishing, ocean acidification, and other effects of climate change on oceans. Marine pollution. Plastic pollution. Overfishing. Protection. Protecting Earth's oceans, ecosystems / against its recognized threats is a major component of environmental protection and is closely related to sustainable development. One of its main techniques is the creation and enforcement of marine protected areas (MPAS). Other techniques may include standardized product certifications, supply chain transparency requirements policies to prevent marine pollution, eco-tariffs, research and development, ecosystem assistance e.g. for coral reefs, support for sustainable seafood e.g. sustainable fishing practices and types of aquaculture, banning and systematically obstructing e.g. via higher costs policies, unsustainable ocean use and associated industries e.g. cruise ship travel, certain shipping practices, monitoring, revising waste management of plastics and fashion industry pollutants, protection of marine resources and components whose extraction or disturbance would cause substantial harm, engagement of broader publics and impacted communities, novel decision-making mechanisms, and the development of ocean cleanup projects. Ocean protection serves to protect human health and to safeguard stable conditions of this natural ecosystem upon which humans depend. It may be necessary to consider marine protection within a national, regional, and international context. Marine protection could also have synergistic effects. For instance, according to a study, a global network of MPA designed to improve fisheries productivity could substantially increase future catch. In 2021, 43 expert scientists published the first scientific framework version that via integration, review, clarifications, and standardization enables the evaluation of levels of protection of marine protected areas and can serve as a guide for any subsequent efforts to improve, plan, and monitor marine protection quality and extents. Examples are the efforts towards the 30% protection goal of the Global Deal for Nature and the UN Sustainable Development Goal 14 Life Below Water. Extraterrestrial oceans. Extraterrestrial oceans may be composed of water or other elements and compounds. The only confirmed large stable bodies of extraterrestrial surface liquids are the lakes of Titan, which are made of hydrocarbons instead of water. However, there is strong evidence for subsurface water oceans' existence elsewhere in the solar system. The best established candidates for subsurface water oceans in the solar system are Jupiter's moons Europa, Ganymede, and Callisto, and Saturn's moons Enceladus and Titan. Although Earth is the only known planet with large stable bodies of liquid water on its surface, and the only one in the solar system, other celestial bodies are thought to have large oceans. In June 2020, NASA scientists reported that it is likely that exoplanets with oceans may be common in the Milky Way galaxy based on mathematical modeling studies. Supercritical fluid on gas giants. The inner structure of gas giants remain poorly understood. Scientists suspect that, under extreme pressure, hydrogen would act as a supercritical fluid, hence the likelihood of oceans of liquid hydrogen deep in the interior of gas giants like Jupiter. Oceans of liquid carbon have been hypothesized to exist on ice giants, notably Neptune and Uranus.
Thank you for watching. Consider supporting the channel, leave a like and subscribe.